Hi everyone, I'm Matteo. Welcome to the very first video on the channel. To kick things off, we are jumping straight into one of the problems from the 2025 STEP exam. STEP is one of the toughest mathematics admissions exams in the UK, and these problems are designed to test real mathematical thinking, not just techniques. Take a moment to read the questions of this exercise, pause the video if you need it, and then we'll solve it together step by step, explaining the ideas behind every move. So let's begin. Okay, so in this question, we have, in the first point, we have a solid of uniform density is formed by rotating through 360 degrees above the y-axis. The region bounded by the part of the curve, and we have this expression for the curve, with x between 0 and r, and what we want that we show the coordinates of the center of mass. Okay, we have a curve that we'll call gamma 1 of this form. Okay, with x between 0 and r. I'm going to write this expression as a function of y. It's going to be this. Okay. Okay, so x, it is quite complicated expression. Okay. So now let's try to make a sketch. It's always useful. Here we have x, here we have y. Okay, so we know that this curve passes through x0, yr, and y0 and r. We know that this curve will pass through 2 points of interest. Okay, so if we put x equal to 0, we have that y is r. While if we put y to 0, we know that x is going to be this expression here, which is r. Okay. We can easily find that this gamma 1 will pass through 0r and r0. Okay, so it's going to be something like this. And when we rotate it around the y-axis, it's going to become, it's very hard to draw, but like a figure, something like that. Okay, so for example, when n equal 2, we know that it's a paraboloid. Okay, now we need to find the center of mass. Okay, the exercise tells us that we only need to find the y-coordinate. Why only y-coordinate? Because if you rotate an object around the axis y, the center of mass will always lie in the xy. And this happens because the contribution in the other axis cancel out because of the symmetry of rotation. So we know that the center of mass is something like that. Okay. Now, how do we find the center of mass? This is going to be the ratio of two integrals that I call a and b. The integral a is, let's start with b, because b is the area of the surface, and here we're going to use the formula of the rotation of the function. So it's going to be pi integral from 0 to r of x squared dy, okay, which x here is the function x to x respect to y, okay? And a is very similar, but we also have a y here, okay? So this is the area, and this is the area weighted by the y-coordinate, okay? Okay, this is like a geometric center of mass. Okay, so now what we need x squared. So x squared is this expression square. Okay, and now we can start integrating finally. So we can start with integral a. Okay. Here, what we can do is that we can take this term out. Okay. And now we can focus only on this integral here that I'm going to call IA. Okay. And IA, okay, is, let's write again, to n. Okay, here I'm going to use the integration by parts, in which the first term is the function that we want to integrate, and the second term is the function that we want to derivate. Okay. So this is going to become okay, so this term here is the integral, so this f, it's the integral of f prime here. Okay, after that we have a minus of this function here. Okay. Okay. Now what we can see here that when y is r, this becomes 0. And when y is 0, this becomes 0. So this is always 0. And we only have the second part here. This one is easy to integrate because it's simply a power, but we need to remember that. So we have the term here, and what we also need, so let's do step by step. This is going to be 2 plus n divided by n plus 1, which is 2 plus 2n divided by n. Okay, and the reciprocal is going to be the term that multiplies the value. Okay, and this, what we have that when y is equal to r, this is 0. Okay, and when y is 0, this becomes this expression here. Okay, so now we can combine everything together. So what we have that a is pi r I, the integral that we just found, okay. Now we need to calculate the integral b. The integral b is it's going to be this integral here. So it's just x squared. So let's take out. We already know there is a part that is going to be out. It's a constant. Okay, and this is very easy to calculate. This is going to be simply r minus y from 2n plus 1, which is 2 plus n divided by n, okay, multiplied by the reciprocal. Okay, and when we do here with this in 0 in r, okay, we need a minus 2. Okay, and this only, we have a contribution only when y is 0, because when y is r becomes r minus y becomes 0. So this integral is going to be simply this value here. Okay, now we can do the ratio finally. Yes, we can do the ratio of a divided by b. Okay, the very nice thing is that this part goes away, so I don't even need to put that. Okay, so what we have n squared divided by n plus 2, 2 plus 2n, this a, okay, divided by this other term here, Okay. This simplify with this simplify with this, and what we are left is n divided by 2 plus 2n, and r, here we can use the property of the powers. Okay. Okay, here's simply a difference. So this is going to be R1. Yes, because it's 2 minus 2, and 2n minus n is n, divided by n is 1. Okay, here we can also take a 2 out of the parentheses. Okay, so first point done. Let's go with the second point. Okay, so now we need to show that the normal to the curve, it's the same. Yes, to the same curve at this point here meets the axis y at this very specific value. Okay, so now let's write again the curve. So have it here, and let's write the point Rp and R1 minus Pn. Okay. And we know that, so this is the point big P, okay? And little p is between 0 and 1, okay? And we know that there is an intersection A in the y-axis of big Y, okay? So the situation is something like this. Okay, we have our curve, we have this point P here, we have the normal, okay, so this is 90 degrees. This normal here cut the y-axis in this point A here. Okay, how do we find the normal to a curve, to a point in a curve? What I'm going to do is I'm going to take the derivative of the curve in that point, which is the slope of the line tangent to the curve in P, and I will use the property of the slopes of two perpendicular lines, which is that if you have a line A, okay, with slope MA, and a line B with slope MB, LA is perpendicular to LB if and only if MA multiplied by, so if the product between MA and MB is minus 1. Okay. And here what I'm going to have the LA is going to be the derivative. Okay. And LB is going to be the normal. Okay. So let's calculate the derivative. The function. So here I need to, it's better if I express the function with respect to y. Okay, now respect to x. Okay. I'm going to take dy over dx, which is going to simply be, it's a very easy derivative. Okay, we are lucky. And to get the slope, which is my MA, okay, I'm going to evaluate the derivative in the point P, okay, So the derivative in the point P I'm going to simply to substitute x with RP. Okay, these two terms cancel out. We have minus n multiplied by p to the power of n minus 1. Okay, so this is my MA. My MB, which is the normal, is minus 1 over MA, which is simply 1 over n to p of 1 minus n. Now we can write the equation of the normal line, because we know that it passes through A and P, and we also have the slope, but we just need one point. So what I'm going to do the equation of the normal, which is y minus yp equal mb x minus xp. Okay, yp is r multiply 1 minus n, and xp is r multiplied by p. Okay. We also have MB, of course. I'm going to. Okay, so MB, YP, XP. But what we want that this equation intersect the x-axis, which means x equal to 0, in order to find our big Y, which is the y-coordinate of the intersection between this normal line and the y-axis. Okay, so we're going to have that big Y is going to be 1 over n, p minus n. So this minus, okay, multiply rp plus r1 minus pn. Okay, and this here, what we can do, let me write this, okay, as it's supposed to be, to get the same result that the exercises shows. Here we can just take one r out, and here we can apply the property of the powers. So this is going to be n minus 1 minus 1, so n minus 2. Okay, this is what we want to find. Let's go to check whether it's the same result. Yes. Perfect. Okay, now they want to show that if n is equal to 4, the greatest value of big Y is r divided by 4. Okay, so here what we can do is, okay, what happens when n is equal to 4? Okay, want to find the maximum value. Okay, we can find the derivative of big Y with respect to what is our variable here. Our parameter is p. Okay, so we can do the derivative of big Y with respect to p, and we put the derivative equal to 0. Okay, here the derivative is 1 is 0. Here is minus 4p to the 3, and here is this other term here. So here, whenever I have something like this. I prefer to write like this because the derivative simply becomes minus s to p of minus n minus 1. Okay, so in this way it's much easier. Here, minus n was minus 2. Okay. Okay, so when this quantity is equal to 0, this quantity is equal to 0 when this term here is equal to 0 because r is different from 0. Okay, and this is going to become something like this, which means that p to the 6 is equal to 1 over 8. Okay. Okay, now, but the problem is that now in big Y, we don't have p to the 6, but we have p to the 4 and p to the second. Okay. But what we know is that if we have p to the 6, okay, if we multiply by 1 over 3, so we raised to 1 over 3, we get that p squared is equal to 1 over 8 1/3, which is 1/2. Okay, and p4 is simply 1 over 2 square, so 1/4. Okay, so now we can put this value in our big Y when n is equal 4, which is going to be r multiplied by 1 minus 1 over 4 minus 1 over 2. Okay, this is going to be exactly 4r divided by 4. Okay, so let's go to the next point. Okay, so the next point say that we have a solid that is formed by rotating through 2 pi about the y-axis. The region bounded by this curve here and this other curve here. Okay, both for x between 0 and r. We have 2 points A and B. The point A is 0 minus r and B is 0 r, which are on the surface of the solid. Okay, we want to show that the solid can rest in equilibrium on a horizontal surface with a vector AB at 3 different non-zero angles to the upward vertical. And we should not attempt to find these angles. Okay, so I think that this is the hardest part of this exercise because it also involves some mechanics to apply. Okay, so now we have 2 curves. The first curve is r to the power 3 multiplied by y equal r to the power 4 minus x to the power 4. And x2 is ry equal minus r squared minus x squared. And we have that x is between 0 and r again. And we also have the point A, 0 minus r, and point B, 0 r, which are on the surface. Okay, so this surface is going to have an upper side, okay, formed by one curve, and the lower side formed by the rotation of the other curve. Here it's really hard to draw, but the idea is that the upper half is composed of the rotation of one curve, the lower half, the bottom half, is composed of the rotation of the other curve. Altogether, they form this solid with this very particular surface. Okay. But the very first thing that we need to do now is that we have this very complicated. We need to find equilibrium points. When we have a complicated object, equilibrium involves the center of mass of this object. So now we need to find the center of mass of these objects that we have here. And again, we need to do the same calculation that we did before. Okay, so let's try to get, for example, we need to find the y center of mass of the object with a rotation of gamma 1, okay, which is going to be, again, two integrals, a divided by b, okay, and we need to find for gamma 2, okay, and the center of mass of the combination of the object, so, okay, con gamma y, gamma 1, 2, okay, this is going to be the weighted average, okay, of the center of the mass in which of the center of the mass of the two objects, in which the weight is the mass of each object. So this is actually what is going to be here, the mass or the area, okay, in this case. So here is going to be it's going to be b gamma 1 multiplied by center of mass of gamma 1 plus b gamma 2 multiplied by the center of mass of gamma 2 divided by the sum of the weights. Okay. Okay, so now what we need to do is we need to calculate those terms. But what can we notice? We don't need to redo everything from scratch, because gamma 1 is exactly the curve that we analyzed before with n equal 4. Okay? And we know the center of mass of the previous object, okay, which is this expression here. Okay, so we need to write this expression with n equal 4. Okay, so sorry, only this expression here. So it's going to be 4. So let's go here. R multiplied by n divided by 2 n plus 1. This one in n equal 4. Which is 2 divided by 5 multiplied by r. After that, what we need to do is we need to find for gamma 2 now. Okay, so let's find, so here we cannot use anything like that for this expression because it's not for n equal 2, because there is a minus here. There is this minus here. Okay, so we can apply the same trick, so we need to do the computation, unfortunately. Okay, so let's calculate B of gamma 2, okay, which is pi from minus r to 0, because now it goes from minus r to 0, of, let's write this expression here as a function of y. So this is going to become r squared plus r epsilon equal x squared. Okay, we actually need x squared. Okay, so this term here is x squared. Okay, as a function of y. Okay, this is very easy to calculate. Okay, and here if you plug in the value, this is going to be pi r third divided by 2. And now what we need to do is we need to find a gamma 2. Okay, so this is going to be very similar, but we also have a y here. Okay, it's extremely similar. The integration here is extremely easy, again, because we only have, it's a polynomial, so it's not complicated. Okay, and here, if you do all the calculation, this is going to be, I mean, we can do when y is 0, this is always 0, so there is only the term with minus r. So here we have a pi r squared divided by 2 plus so this is going to be r4 divided by 3, but okay, there's also 2 here, and I think that there is a minus here. Okay, so a gamma 2 is pi. Okay, 3 r fourth minus 4 r fourth, which is going to be minus pi r fourth divided by 6. Okay, so now we can find y of gamma 2, the center of the y coordinate of the center of mass of gamma 2, which is a gamma 2 divided by gamma 2, which is going to be minus pi r4 6 divided by pi r3 2. Pi away. These are third cancel out here. These two cancel out here. So what remains is going to be minus r divided by 3. So the center of mass of the second curve is below 0, and this is quite expected because it's going to be somewhere here. So this is going to be the center of mass of gamma 2. And here we have the center of mass of gamma 1. And now we want to know where is the center of mass of the composite object. It's going to be above or below y equal to 0. We can do the calculation. So now we can apply this formula here, the weighted average, okay? And this is going to become, so here we have the mass of the first object, multiplied by the center of mass of the first object, plus the mass of the second object. When I say mass, I always intend the denominator of the center of mass computation. Plus multiplied by the center of mass. Here it's important to remember the sign, okay? So here it's a minus, okay? Multiplied by the sum of the weights. Okay, here a lot of things goes away, pi. Here we have this r square, r to the power of 3 here, that goes away. Okay, so what we have an r here. We have 4 divided by 15 minus 1 divided by 3. And here we have 2 divided by 3 plus 1 divided by 2. Okay. So here it's 30, the minimum common denominator. See. Oh, here I made a mistake. Okay, here there is not 2 to simplify. So here it's 1 over 6. Now 1 over 3. Okay. Okay. And this is going to be 3 divided 35r. Okay, so the center of mass of the composite object is above that 0. So it's somewhere around here. Okay, now I will say probably the most complicated part, because now the exercise asks to find the angles at which the object is in equilibrium when we lay down the object on a horizontal surface. So if this is the surface, and this is our composite object. Okay, so what we know that the center of mass of this object is along the y-axis. Okay, so here we have the 0 of the y-axis, and here we have the center of mass. Okay, so now what are the points that enforce the equilibrium of the object? The object is in equilibrium if the normal, so the object is in equilibrium if the normal, okay, from the contact point pass through the center of mass. If these satisfy, the object is in equilibrium. So what we need to find the points along this surface that, if we trace the normal of the point at this surface, the normal will pass through the center of mass. Okay? Because what happens, for example, if you have this situation here. So let's imagine that this is our object. Okay, the center of mass is here. Okay, but the normal of the contact point is something like that. So what happens in this case is that here you have your gravity, mg, okay, and your gravity exerts a torque to the object that makes the object rotating and moving. Because here you have a force, here you have the distance of the force. At this distance, this discrepancy between the projection of the normal line and the location of the center of mass creates a torque that makes the object moving. We need that, the intersection of normal at y-axis is equal to the y or the y coordinate of the center of mass of the composite object. Here, the situation is a little bit more complicated because a part of the solid is composed by gamma 2 and the other part is composed by gamma 1. So we need to consider both. So we need to consider the possibilities of the normal lines using either gamma 1 and gamma 2. Because if you have a point here, we are going to use gamma 1. But if you have a point here, we need to use gamma 2. Okay? Okay, so what is the intersection of the normal line to the y coordinate, to the y-axis? Was our big Y that we found before. Okay, so for a general n, okay, it's this quantity here. We know that the first curve is the same as the original problem with n equal 4. Okay, what is what we found before. So what's this expression here? And this has to be equal to the y coordinate of the center of mass of the composite object. Okay, this is for gamma 1. For gamma 2, okay, actually, I realized that gamma 2 is related with the the original curve in function of n, with the difference that if you go here, so you see that this is very similar to the original function for n equal 2, but there is a reflection here, okay, of the sign of the y coordinate. So it's like a reflected n equal 2, okay? Which means that the big Y for gamma 2 is this expression for n equal 2 and after the inversion of sign. Okay, so it's going to be minus because there is the reflection r of 1 minus p squared minus 1 over 2, and that's it, because it's p to 0 equal the same expression here. And now, okay, we need to solve these two equations. Okay, we can simplify the r, and for the first one we have so here I was going to do p6 minus 1 equals 0. This means that this to be equal to 0 means that 140 p6 minus 128 p squared plus 45 is equal to 0. Okay, this is a very complicated question. But what we can do is that we can use a substitution like u equal p square. This equation becomes a cubic equation. Okay. Still very hard to resolve, but what we can do is, let's see what is the behavior of this function here that I'm going to call y du, okay, of the cubic, with respect to u or p. Okay, so here this is either u or p. Okay, we know that p goes from 0 to 1. Okay, so u will go from 0 to 1 as well. Okay, when when we plug in 0 in y, we had that y of 0 is 35, which is greater than 0. When you plug in 1, we have 130 minus 128 plus 45, and this quantity is definitely greater than 0. So we start from here, and we go back, and we are around here. Okay, so now to check whether this equation has any solutions, we need to see whether there is a point in which the cubic is below that 0. We tried 0, we try 1. Let's try let's try in the half. Okay, so for example, let's try 1/2. What happens? So in 1/2, what you're going to have, we're going to have 130 multiplied by 1/8 minus 128, 2 plus 35. 130 divided by 8 is, let me check. Okay, 17.5 minus 64 plus 35. And this is below 0. Okay, we got extremely lucky because we know that at 1/2 we are below 0. So this function y du, okay, was green, will do something like this. Which means that there are two intersections with a 0. So this equation has two solutions. Okay, in p from 0 to 1. Okay, we don't need to know the exact value. And now we can check the second equation for gamma 2, which is much simpler because this equation is simply pi squared plus 1/2 minus 1 equal 3 divided by 35. In this case, this is going to be p squared minus half minus equal 3 divided by 45. So p squared is 76 plus 35, which is 41 divided by 70. So the absolute value of p is equal to the square root, okay, which means that p is equal plus minus. But we know that p is between 0 and 1. So that means that we can only accept the positive root. And this quantity is definitely below 1. And this is the one solution. So 2 plus 1, we got the 3 solutions. Thank you for watching all all the exercise have been quite challenging, honestly, considering that uh, people have 3 hours to make 6 exercises of this type. So you're supposed to take around half an hour to resolve one of these, at least if you want to resolve all of it. And in this case, I try to go a little bit slow, try to explain each step, and I hope that this could be useful for you. If you are interested in content of this type, let me know and I will try to solve other exercises like that. But I'm planning to do uh, different types of videos, so not just simply solving challenging exercises in admission exams, but also do uh, courses or do any kind of exercises in mathematics and physics. Thank you.